Every astronaut who returns from the International Space Station comes back slightly younger than they would have been on Earth. It's not science fiction, it's measured fact. Atomic clocks have measured microsecond-scale differences on long-duration ISS missions, with astronauts experiencing approximately 0.01 seconds of time dilation during a typical 6-month stay. The difference is microscopic, but it's real and measurable with atomic precision. This isn't just a curiosity. It's proof that time itself is not what we think it is. Einstein predicted this over a century ago with nothing but pure thought, and today's technology has turned his wildest theories into everyday reality. But how did one man's simple observation change everything we thought we knew about time? The patent clerk's revolutionary moment. In 1905, Albert Einstein worked as a patent clerk in Bern, Switzerland, spending his days reviewing applications for electrical devices and mechanical contraptions. But his mind was elsewhere, grappling with physics questions that had tormented him for years. Einstein used his daily tram commutes to escape into the abstract realm of theoretical physics, and it was during one of these routine journeys that he conceived a thought experiment that would revolutionize modern physics forever. The Ziklag clock tower dominated Bern's skyline, its massive hands marking the steady passage of time for the entire city. Einstein had passed this medieval timepiece thousands of times, but as his tram pulled away from the station that evening, something different stirred in his thoughts. He watched the clock tower grow smaller in the distance as the tram gained speed, and the physics problem that had been eating at him for months suddenly crystallized into a single piercing question. What would happen if this tram could somehow accelerate to the speed of light itself? Einstein closed his eyes and let his imagination run wild. In his mind, the tram accelerated faster and faster, reaching velocities no machine had ever achieved. At 299,792 kilometers per second, something extraordinary happened to his view of the clock tower. He realized that at light speed, a distant clock would appear stopped, even as it continued ticking at the tower, showing time must slow with motion. Yet Einstein knew with absolute certainty that back at the tower, citizens of Bern continued to observe the clock hands moving at their regular intervals, marking seconds and minutes as they always had. This visualization struck Einstein like a thunderbolt. The implications crashed over him in waves. Time was not the universal constant that Newton had assumed. Time could slow down, speed up, or even freeze depending on how fast you moved through space. The faster you traveled, the slower time became relative to everything you left behind. Motion through space directly controlled motion through time. Einstein opened his eyes and stared out at the real clock tower, now just a distant speck in the evening light. His mind raced through the logical consequences of this thought experiment. If motion through space affected the passage of time, then time itself must be flexible, malleable, subject to the same physical laws that govern everything else in the universe. This meant that two observers moving at different speeds would experience time at different rates, even though both would perceive their own clocks as running normally. The patent clerk who spent his days analyzing mechanical inventions had just stumbled upon the most revolutionary concept in the history of physics. The two dimensions that humans had always considered completely separate were actually connected in the most fundamental way possible. Increase your speed through space, and you decrease your speed through time. The relationship was not just theoretical. It was mathematical, precise, and absolute. Einstein gripped the tram's handrail as the full weight of his discovery settled in. If time could slow down under certain conditions, what other assumptions about reality were completely wrong? Perhaps space itself was not the rigid, unchanging stage that Newton described. Perhaps the very fabric of the universe was far more dynamic and interconnected than anyone had imagined. The questions multiplied faster than he could process them, each one opening new doors to mysteries that would reshape human understanding of existence itself. This simple thought experiment aboard a Bern tram would eventually become the foundation for technologies that define modern life. Today's GPS satellites must account for Einstein's time dilation predictions every single day to maintain their accuracy. Without corrections based on his 1905 insight, navigation systems would drift by miles within hours, making precise location impossible. The same theories guide particle accelerators that probe the deepest secrets of matter, enable atomic clocks that synchronize global communications, and explain phenomena observed in the most distant reaches of space. Einstein's mental journey from frozen clock hands to flexible time revealed a hidden conflict at the heart of physics. As the tram continued its route through Bern's narrow streets, Einstein's thoughts had already leaped beyond the boundaries of his century. He sensed that his discovery would require abandoning humanity's most basic assumptions about the nature of reality, but he could not yet see the full scope of the battle that lay ahead. The patent clerk stepped off the tram and walked toward his apartment, but his mind remained fixed on the implications of his revelation. That frozen clock tower had shown him something profound about the structure of the universe. Space and time were not separate, independent dimensions, but part of a unified fabric that could bend, stretch, and warp. Einstein knew he had uncovered something that would challenge every physicist's understanding of reality, but the path forward would demand confronting a fundamental contradiction that had been hiding in plain sight for decades. When giants collide, Newton versus Maxwell, Einstein's mental battle pitted two intellectual giants against each other in the most fundamental way possible. Isaac Newton had established that all velocities are relative, never absolute, requiring the phrase with respect to for any meaningful measurement. James Clerk Maxwell had discovered that light travels at exactly 299,792,458 meters per second, according to his electromagnetic equations, maintaining this speed regardless of the observer's motion. These discoveries seemed to contradict each other at the most basic level, creating a puzzle that would torment Einstein for years. Newton's breakthrough had proven that every measurement of speed depends entirely on the chosen reference frame. A car driving at 60 miles per hour moves at only 20 miles per hour with respect to another car traveling 40 miles per hour in the same direction. This relativity extends throughout the cosmos. The International Space Station orbits Earth at 17,500 miles per hour with respect to the planet's surface, yet Earth itself hurtles through space at 67,000 miles per hour with respect to the Sun. Sun races through the Milky Way galaxy at 514,000 miles per hour respect to the galactic center. Newton's laws insisted that no single reference frame possessed special status, and motion could only be described in terms of relationships between objects. Maxwell's electromagnetic theory presented a completely different picture. Through mathematical analysis of electric and magnetic fields, Maxwell determined that electromagnetic waves, including light, propagate at a fixed speed through space. The speed appeared universal, unchanging, and absolute. Unlike the relative velocities Newton described, light seemed to maintain its precise pace regardless of who measured it or how they moved through space. A scientist standing motionless would measure light at this exact speed. An astronaut racing through space in the opposite direction would measure exactly the same speed. The contradiction struck at the heart of physics. If Newton's laws truly govern all motion in the universe, then light should obey the same rules as trains, cars, and spacecraft. The speed of light should vary depending on the observer's reference frame. A person moving toward a light source should measure a faster speed, while someone moving away should measure a slower speed. Yet Maxwell's equations revealed no such variation. Light maintained its constant speed in every measurement, under every condition, from every possible reference frame. Modern precision instruments have confirmed Maxwell's predictions with extraordinary accuracy. The current definition of the meter itself derives from the speed of light, fixing it at exactly 299,792,458 meters per second by international agreement. Laser interferometry systems can measure light speed variations smaller than 1 part in a trillion. Yet no variation has ever been detected. Atomic clocks depend on light, maintaining its exact speed regardless of Earth's rotation, orbital motion, or the movement of measuring equipment. Particle accelerator experiments reveal the same paradox. Scientists accelerate subatomic particles to velocities approaching light speed, then measure the speed of photons emitted by these racing particles. Newton's laws predict that photons emitted in the forward direction should travel faster than the standard light speed, while photons emitted backward should travel slower. The particles act as moving light sources, and their velocity should add to or subtract from the photon's speed. Yet every measurement confirms that all photons travel at exactly 299,792,458 meters per second, regardless of the source particle's velocity or direction of emission. This creates an impossible situation for traditional physics. High-energy particles racing through accelerator tunnels should behave like speeding trains, adding their velocity to anything they emit. When a person throws a ball forward from a moving train, the ball's speed equals the throw velocity plus the train's velocity with respect to the ground. When particles emit light while traveling at tremendous speeds, The same principle should apply. The photon should inherit some of the particle's velocity, creating measurable deviations in light speed. The complete absence of such deviations contradicts everything Newton's laws predict about relative motion. Einstein faced an impossible choice between two pillars of physics. Either Newton was fundamentally wrong about the relative nature of all velocities, or Maxwell was fundamentally wrong about light speed being constant. Abandoning Newton's laws would destroy the foundation of mechanics, making it impossible to predict the motion of planets, projectiles, or any moving object. Abandoning Maxwell's laws would eliminate the theoretical basis for electricity, magnetism, and electromagnetic waves, including light itself. Both frameworks have been tested countless times and formed the bedrock of scientific understanding. Yet one of them had to be wrong, or something else entirely had to give way. The conflict between relative motion and absolute light speed created a logical contradiction that traditional physics could not resolve. Einstein realized that solving this puzzle would require abandoning one of humanity's most basic assumptions about the nature of reality itself. The answer would demand accepting something far stranger than either Newton or Maxwell had ever imagined. To expose the deeper implications of this conflict, Einstein would need to construct another thought experiment that would reveal just how profound the consequences truly were. The lightning strike paradox. Einstein constructed his famous train and embankment thought experiment to expose this fundamental conflict. He positioned himself at the center of a train platform, equidistant from both ends. Two lightning bolts struck simultaneously at the platform's opposite extremes, creating brilliant flashes that illuminated the entire station. Einstein's perfect positioning ensured that light from both strikes traveled identical distances to reach him. The beams arrived at his location at precisely the same moment, confirming that the lightning strikes had occurred simultaneously. The light from each strike covered exactly the same speed, reaching Einstein's eyes together. This simultaneity seemed obvious and absolute. Both lightning bolts had struck at the same instant, creating two events that occurred in perfect synchronization. Einstein could measure the time interval between the strikes as 0. Einstein then introduced a complication that would shatter this simple picture. A passenger train raced past a platform at tremendous speed, carrying an observer who witnessed the same lightning strikes from a dramatically different reference frame. This passenger sat in the exact center of the train car, maintaining the same geometric relationship to the lightning strikes that Einstein held on the platform. The critical difference lay in motion. While Einstein remained stationary on the platform, the train passenger hurtled through space at enormous velocity. This motion fundamentally altered what the passenger would observe about the timing of the lightning strikes. The passenger would not witness the strikes as simultaneous events, even though both observers maintained identical positions relative to the lightning bolts. The light from the strike at the front of the train's direction would reach the passenger first. Since the train moved toward this lightning bolt, the distance that light needed to travel became shorter. Meanwhile, the light from the rear strike faced a longer journey because the train carried the passenger away from that flash. The moving observer would see one lightning bolt before the other, creating a clear sequence of events rather than simultaneity. This difference in observation created a devastating logical problem. The passenger would measure a specific time interval between seeing the two flashes. Einstein on the platform would measure 0 time interval, seeing the flashes simultaneously. The same physical events produced different measurements depending on the observer's motion. Both observers were equally valid, equally positioned, and equally capable of making accurate measurements. The implications revealed that simultaneity depends entirely on the observer's reference frame. Events that appear simultaneous to one observer occur in sequence for another observer moving at different velocity. This relativity of simultaneity contradicted humanity's most basic assumptions about time. Simultaneity had always been considered absolute, a fundamental property of events that remained the same regardless of who observed them. The paradox created an impossible situation for traditional physics. If light speed remained constant as Maxwell's equations demanded, then simultaneity could not be absolute. If simultaneity was absolute as Newton's framework assumed, then light speed could not remain constant for all observers. The train, passenger, and platform observer could not both be correct about the timing of identical events using conventional physics. Modern particle accelerators provide real demonstrations of these effects with subatomic particles traveling at velocities approaching light speed. Scientists observe particles emitting light while racing through accelerator tunnels at tremendous velocities. These particles act as moving light sources, similar to Einstein's thought experiment, but with measurable, quantifiable results. The emitted light maintains Maxwell's constant speed regardless of the particle's motion, confirming that light speed does not follow Newton's rules of relative velocity. Experiments at facilities like CERN create conditions where particles move fast enough for relativistic effects to become clearly observable. High-energy particle collisions generate debris that races away from collision points at different velocities. Scientists can measure the timing of light signals from these moving sources, testing whether simultaneity depends on the observer's reference frame. The results consistently confirm Einstein's predictions about the relativity of simultaneity. Quantum physics research has validated these observations at the subatomic level with unprecedented precision. Modern detectors can measure time intervals down to attoseconds, revealing how particle interactions that appear simultaneous from one reference frame occur in sequence from another. These measurements validate Einstein's insight that simultaneity depends entirely on the observer's motion through space. The Large Hadron Collider continues searching for any violations of these principles that might indicate preferred reference frames in spacetime. Scientists examine millions of particle collisions looking for evidence that certain directions in space might be special, which would restore absolute simultaneity. No such evidence has been found despite extraordinary measurement precision. Every experiment confirms that simultaneity remains relative to the observer's motion. Einstein's lightning strike thought experiment proved that Newton's relative motion and Maxwell's constant light speed could not both be correct under traditional assumptions about space and time. The train passenger and platform observer produced contradictory measurements of identical events. Their conflicting observations demanded a revolutionary solution that would challenge every physicist's understanding of reality. Einstein faced a choice that would force him to abandon fundamental principles that had governed physics for centuries, or discover something even more profound about the nature of time itself. Einstein faced an impossible choice between two pillars of physics. Newton's laws had explained planetary motion and mechanical systems for centuries, while Maxwell's equations had revealed the nature of light and unified electricity with magnetism. Choosing Newton meant accepting that light speed varied with motion, destroying electromagnetic theory. Choosing Maxwell meant accepting constant light speed, which would demolish the principle of relative velocities in cripple mechanics. Then Einstein conceived a revolutionary possibility that no one else had considered. What if both Newton and Maxwell were correct, but something else entirely needed to change? What if the conflict arose not from errors in their theories, but from wrong assumptions about the nature of space and time themselves? Perhaps reality operated according to rules far stranger than humans had ever imagined. Einstein proposed that time itself must be flexible rather than rigid. Instead of flowing at a constant rate throughout the universe, time could stretch and compress depending on motion and gravity. This elasticity would allow light to maintain its constant speed while preserving the principle of relative motion. Time would adjust its pace to ensure that light always traveled at 299,792,458 meters per second from every observer's perspective, regardless of their motion through space. This solution seemed completely absurd to every physicist of Einstein's generation. Time had always been considered the most fundamental constant in the universe. Newton described time as flowing uniformly everywhere, creating a universal rhythm that synchronized all events throughout space. Clocks might run fast or slow due to mechanical imperfections, but time itself remained steady and unchanging. The idea that time could vary seemed to violate the most basic assumptions about reality. Einstein's proposal challenged humanity's intuitions about existence. If time could slow down or speed up, then the ordered progression of cause and effect became relative to the observer. Events that appeared simultaneous from one perspective could occur in sequence from another. The universal timeline that connected all events throughout history would fragment into multiple timelines depending on motion and gravity. Reality would become far more complex and interconnected than anyone had suspected. GPS satellites provide daily proof that Einstein's solution actually governs reality. Each satellite carries atomic clocks that experience time dilation due to their orbital velocity of 17,500 miles per hour. Special relativity predicts these high-speed clocks should run slower than Earth-based clocks. Simultaneously, the weaker gravity at orbital altitude creates gravitational time dilation that makes the satellite clocks run faster. These competing effects produce a net time difference of approximately 38 microseconds per day. Without corrections for these relativistic effects, GPS positioning would become completely unreliable within hours. Errors would accumulate at rates exceeding 10 kilometers per day, making navigation impossible. Engineers solved this problem by adjusting the satellite clock frequencies before launch. The fundamental frequency of GPS atomic clocks is set to 10.229999543 MHz instead of the standard 10.23 MHz, creating an offset that compensates for relativistic time dilation effects. This frequency adjustment represents one of the most practical applications of Einstein's revolutionary insight. The offset factor of plus 4.465 times 10 to the power of negative 10 ensures that satellite clocks maintain synchronization with ground-based atomic standards despite experiencing different rates of time passage. GPS systems perform millions of these relativistic corrections every day, proving that time dilation is not just theoretical but essential for modern technology to function. The precision required for GPS accuracy demands nanosecond-level timing synchronization between satellites and ground stations. If relativistic effects were ignored, the accumulated timing errors would destroy the system's ability to determine positions accurately. This technological requirement validates Einstein's prediction that time must be flexible to maintain light speed as a universal constant. The Atomic Clock Ensemble in Space mission, launched in April 2025, tests gravitational time dilation with unprecedented accuracy by comparing atomic clocks on the International Space Station with identical clocks on Earth's surface. The ACES mission measures time variations across 10 sessions, each lasting 25 days, with precision down to 1 part in 10 to the power of 17. Einstein's breakthrough established the concept of time dilation as a measurable physical phenomenon. Time literally runs at different rates depending on velocity and gravitational field strength. Astronauts on the International Space Station age slightly slower than people on Earth's surface due to their high orbital speed. Mountain climbers experience slightly faster time passage than people at sea level due to weaker gravitational effects at higher altitudes. These differences are microscopic but real and measurable with modern instruments. The revolutionary concept that emerged from Einstein's impossible choice became known as special relativity. This theory unified space and time into a single four-dimensional framework called spacetime, where motion through space directly affects motion through time. The theory preserved both Newton's principle of relative motion and Maxwell's constant light speed by allowing time itself to be relative rather than absolute. Special relativity transformed physics by revealing that space and time were not separate, independent dimensions, but components of a unified structure. The patent clerk who refused to choose between Newton and Maxwell had discovered that the universe operated on principles
Time
that would
becomes
fundamentally reshape
elastic.
human understanding of reality
Einstein's
itself.
mathematical
framework revealed exactly how this flexibility operated in practice. Time dilation followed precise equations that could predict exactly how much clocks would slow down based on velocity and gravitational field strength. The faster an object moved through space, the more dramatically time would stretch, causing clocks to run slower relative to stationary observers. This relationship wasn't random or approximate, but followed exact mathematical laws that governed the behavior of space-time itself. The International Space Station provides a perfect laboratory for observing this time elasticity in action. Astronauts aboard the ISS traveled approximately 17,500 miles per hour, experiencing measurable time dilation effects due to their high orbital velocity. Time passes slightly slower for these astronauts compared to people on Earth's surface. From their perspective, time flows normally, but precise atomic clocks reveal that they age at a different rate than Earth-bound observers. This effect demonstrates Einstein's prediction that motion through space directly affects the passage of time. The Atomic Clock Ensemble in Space mission, launched in April 2025, compares highly accurate atomic clocks aboard the ISS with identical clocks on Earth's surface. This mission measures gravitational time dilation with unprecedented precision by operating atomic clocks that were miniaturized from laboratory size to the size of a small refrigerator. The engineering achievement required to create these compact yet incredibly precise instruments represents a major breakthrough in space-based physics experiments. The ACES mission operates across 10 sessions, each lasting 25 days, and is controlled from the Columbus Control Center in Munich, Germany. These extended measurement periods allow scientists to accumulate data about time dilation effects over months of continuous operation. The mission's 30-month duration provides sufficient time to detect even the smallest variations in time passage between orbital and terrestrial environments. The measurements reveal exactly how much time stretches due to the combination of high velocity and reduced gravitational field strength at orbital altitude. Einstein's elastic time concept revolutionized physics by revealing that time deserved recognition as a fundamental dimension of reality. Rather than treating time as a universal constant that provided the backdrop for physical events, Einstein proposed that time was an active participant in the structure of the universe. Time could be affected by motion and gravity just like any other physical quantity. This insight elevated time from a mere measurement tool to a dynamic component of the cosmos itself. The revolutionary proposal that emerged from this understanding unified space and time into a single four-dimensional fabric called space-time. Instead of viewing space and time as separate independent dimensions, Einstein showed that they were intimately connected aspects of a unified structure. Motion through space created motion through time, linking the two dimensions in a mathematical relationship that could be precisely calculated. This space-time framework provided a complete description of how objects move through both spatial and temporal dimensions simultaneously. The space-time concept explained phenomena that Newton's absolute time and space could never account for. Gravitational effects, electromagnetic wave propagation, and high-velocity particle behavior all became comprehensible within the space-time framework. Scientists could predict how clocks would behave in different gravitational fields, how light would travel between moving objects, and how particles would interact at extreme velocities. The mathematical tools of space-time geometry provided solutions to problems that had puzzled physicists for decades. Mars missions illustrate the practical implications of elastic time for future space exploration. Astronauts on a 21-month journey to Mars would experience measurable time dilation effects due to their high velocity during transit. While the difference amounts to only a few nanoseconds compared to Earth observers, the effect demonstrates that time passage varies even for relatively modest space travel. Extended stays on Mars would create additional time dilation effects due to the planet's different gravitational field strength compared to Earth. The long-term implications become more significant for permanent Mars colonists. A human living 80 years on Mars would experience approximately 12 seconds less time than someone living exactly 80 years on Earth. This difference results from Mars having weaker gravity than Earth, causing time to pass slightly faster on the red planet's surface. While 12 seconds represents a tiny fraction of a human lifetime, it demonstrates that time passage varies throughout the solar system depending on local gravitational conditions. These measurements validate Einstein's insight that reality operates according to principles far stranger than common sense suggests. Time responds to motion and gravity like any other physical quantity. Clocks run at different rates depending on their velocity and location in gravitational fields. The universe maintains precise mathematical relationships between space, time, motion, and gravity that determine how physical processes unfold. The elastic nature of time means that simultaneity becomes relative to the observer's motion and gravitational environment. Events that appear simultaneous from one perspective can occur in sequence from another. The ordered progression of cause and effect varies depending on the observer's reference frame. This flexibility allows the universe to maintain consistent physical laws while accommodating the strange requirements of relativistic physics. Einstein's discovery that time could stretch and compress revealed that the space-time fabric itself was far more dynamic than humans had ever imagined. The rigid, mechanical universe that Newton described gave way to a cosmos where space and time formed a unified structure that could bend and warp. But Einstein's revolutionary insights about space-time would soon reveal an even more profound mystery about the fundamental forces that shape reality itself. Gravity's hidden secret. Newton described gravity as a mysterious force that reached across empty space to pull objects together. The sun somehow attracted Earth from 93 million miles away without any visible connection between them. Apples fell from trees because Earth exerted an invisible pull on them through the vacuum of space. This concept worked perfectly for calculating planetary orbits and predicting motion, but it left a fundamental question unanswered. How could massive objects influence each other across vast distances of nothingness? What mechanism allowed this force to operate through empty space without any physical medium to carry it? Einstein proposed a revolutionary alternative that eliminated the need for mysterious forces acting at a distance. Massive objects like the sun do not pull on surrounding matter through some invisible force. Instead, they curve the fabric of space-time itself, creating geometric distortions that guide the motion of nearby objects. Mass warps the structure of reality, bending the four-dimensional framework of space and time into curves, valleys, and hills that determine how everything moves through the universe. The standard model for visualizing this concept involves imagining space-time as a flexible rubber sheet stretched flat. This represents the undisturbed fabric of space-time in empty regions of the universe. When a massive object like the sun sits on this sheet, it creates a depression that warps the flat surface into a curved valley, extending outward from the object's position. The greater the object's mass, the deeper and steeper the depression becomes. This curved geometry represents how massive objects form space-time around them. Objects moving through this curved space-time naturally follow the contours created by these depressions. They appear to be pulled toward massive objects, but no force actually attracts them. The objects simply follow the straightest possible paths through the curved geometry of warped space-time. What we perceive as gravitational attraction is actually objects moving along the curved pathways that mass creates in the four-dimensional fabric of reality. Planets orbit stars not because of any pulling force, but because the curved space-time guides their motion into elliptical trajectories. Earth's enormous mass creates a steep valley in space-time with the deepest point located at the planet's center. This valley becomes progressively shallower as distance from Earth increases, creating weaker gravitational effects at higher altitudes. Objects near Earth's surface experience strong curvature effects because they sit deep within this space-time valley. Satellites in orbit occupy regions where the valley is less steep, experiencing weaker gravitational effects that allow them to maintain stable orbital trajectories around the planet. The curvature varies dramatically with distance from massive objects, following precise mathematical relationships that Einstein calculated. This variation explains why astronauts on the International Space Station experience microgravity despite being only 250 miles above Earth's surface. They orbit within a region of space-time where Earth's gravitational valley is shallow enough to allow continuous free fall around the planet. The same principle applies throughout the solar system, where planets orbit the sun by following curved paths through the space-time valley created by the sun's massive bulk. Gravitational wave detectors in 2025 can measure ripples in space-time with extraordinary precision. The Laser Interferometer, Gravitational Wave Observatory, and the Virgo detector monitor space-time. Distortions smaller than 1/10,000th the width of a proton. These instruments detect the passage of gravitational waves created when massive objects like black holes or neutron stars accelerate through space, creating ripples that propagate outward through space-time at light speed. The successful detection of these waves provides direct evidence that space-time behaves exactly as Einstein predicted. Recent observations of black holes have confirmed Einstein's predictions about extreme space-time curvature. The Event Horizon Telescope captured images of the supermassive black holes at the center of galaxy M87, revealing the shadow cast by the black hole's event horizon against the glowing matter spiraling around it. This shadow appears exactly as Einstein's equations predict for an object so massive that it creates nearly infinite curvature in space-time. The light from matter approaching the black hole follows the curved space-time paths, creating the distinctive patterns observed in these historic images. Black holes represent the most extreme example of space-time curvature possible in the universe. Their massive density creates such steep valleys in space-time that nothing, not even light, can escape once it falls past the event horizon. The curvature becomes so severe that it essentially creates a one-way path through space-time, allowing matter and energy to fall inward, preventing anything from traveling back outward. These extreme conditions provide natural laboratories for testing Einstein's most radical predictions about the behavior of curved space-time. This curved space-time concept leads directly to gravitational time dilation effects that influence every moment of our lives. Time passes at different rates depending on the depth of the gravitational valley an observer occupies. Clocks run slower in stronger gravitational fields because time itself follows the curvature of space-time. The deeper an observer sits within a massive object space-time valley, the more slowly time passes relative to observers in weaker gravitational fields at greater distances. Even on Earth's surface, precision instruments can detect time differences caused by elevation changes of just a few meters. Atomic clocks at sea level run measurably slower than identical clocks on mountaintops because sea level positions sit deeper within Earth's gravitational valley. The Atomic Clock Ensemble and Space Mission, launched in April 2025, tests these effects by comparing atomic clocks aboard the International Space Station with identical clocks on Earth's surface. These measurements reveal exactly how gravitational curvature affects the passage of time throughout different regions of Earth's space-time valley. Einstein's insight transformed gravity from a mysterious force into geometric properties of space-time itself. Mass and energy curve the fabric of reality, creating the paths that all matter and energy must follow. This geometric understanding revealed that the most extreme gravitational environments in the universe would produce the most dramatic demonstrations of time dilation effects where the passage of time could slow to almost unimaginable degrees. The interstellar effect. The movie Interstellar presented audiences with one of the most dramatic demonstrations of time dilation ever depicted on screen. Astronauts descended to a planet orbiting dangerously close to a massive black hole, where the gravitational effects created extreme time distortion. Every hour spent on that planet's surface equaled 7 years passing on Earth. The crew members who remained on the spacecraft watched decades slip away while their colleagues experienced only a few hours on the planet below. This scenario represents a completely accurate portrayal of Einstein's gravitational time dilation predictions. The planet in Interstellar experiences such intense gravitational effects because it sits deep within the black hole spacetime valley. The massive black hole warps spacetime so severely around the planet that time itself slows to a crawl compared to regions with weaker gravitational fields. This extreme time dilation occurs because the planet occupies a position where spacetime curvature reaches enormous proportions. The gravitational field strength becomes so powerful that it dramatically affects the fundamental rate at which time passes for anything on the planet's surface. This dramatic time difference follows directly from Einstein's field equations, which describe how mass and energy curve spacetime. When applied to the extreme conditions near black holes, these equations predict exactly the kind of time dilation effects shown in the movie. The precision of Einstein's predictions allows scientists to calculate these effects with mathematical certainty. Black holes create the most extreme space-time curvature possible in the universe, leading to the most massive time dilation effects found anywhere in nature. Their enormous mass compressed into incredibly small volumes generates gravitational fields so intense that they warp space-time beyond anything found around normal stars or planets. Near a black hole's event horizon, time dilation becomes so extreme that an outside observer would see time essentially stop for anything falling toward the black hole. The Event Horizon Telescope's observations of real black holes have provided unprecedented measurements of time dilation effects in their vicinity. Scientists can now observe matter spiraling around black holes and measure how time passes differently at various distances from these massive objects. Gas and debris orbiting close to black holes show clear signatures of time dilation, with material closer to the black hole appearing to move and emit light at rates that differ dramatically from material farther away. These observations reveal space-time curvature gradients that create measurable time differences across relatively small distances near black holes. Matter on the inner edge of an accretion disk experiences significantly different time passage compared to matter on the outer edge. The time dilation effect creates observable differences in the frequency and timing of light emitted from different regions around the black hole, providing direct evidence of Einstein's predictions about extreme gravitational environments. Different planets throughout the universe with varying masses create their own unique gravitational time dilation effects. Jupiter's massive bulk generates stronger gravitational fields than Earth, causing time to pass slightly slower on Jupiter's surface compared to Earth's surface. Mars, with its smaller mass, creates weaker gravitational effects that allow time to pass slightly faster than on Earth. These differences become measurable when comparing atomic clocks placed on different planetary surfaces. The relationship between planetary mass and time dilation follows Einstein's equations precisely. More massive planets create deeper space-time valleys, resulting in stronger time dilation effects for observers on their surfaces. Less massive planets create shallower valleys, allowing time to pass at rates closer to what distant observers would measure in empty space. Earth's gravity creates measurable time differences between sea level and mountain peaks, demonstrating that gravitational time dilation operates continuously in our everyday environment. Atomic clocks at sea level run measurably slower than identical clocks placed on high mountains because sea level positions sit deeper within Earth's gravitational field. The National Institute of Standards and Technology has measured these effects by comparing atomic clocks at different elevations, finding time differences that match Einstein's predictions exactly. Mount Everest summit experiences time passage approximately 25 nanoseconds per day faster than sea level due to the weaker gravitational field at that altitude. This difference results from being roughly 29,000 feet farther from Earth's center, placing observers in a slightly shallower region of Earth's spacetime valley. Precision atomic clocks can detect these tiny variations, proving that gravitational time dilation operates at every elevation on Earth's surface. Precision instruments in 2025 can detect time differences caused by elevation changes of just a few meters. The Atomic Clock Ensemble in Space mission measures gravitational time dilation between the International Space Station and Earth's surface with unprecedented accuracy. These measurements reveal time differences corresponding to elevation changes as small as the height of a typical building, demonstrating the incredible sensitivity of modern atomic clocks to gravitational effects. Laboratory experiments now routinely measure gravitational time dilation by comparing atomic clocks at different floors of the same building. Clocks on upper floors run measurably faster than clocks in basements because they experience slightly weaker gravitational fields. These experiments validate Einstein's predictions about gravitational time dilation operating at the smallest measurable scales. The most mind-bending realization emerging from these measurements is that your head literally ages faster than your feet due to gravitational time dilation. Your head sits approximately 6 feet farther from Earth's center than your feet, placing it in a slightly weaker gravitational field where time passes faster. The difference amounts to roughly 90 billionths of a second per year, demonstrating that gravitational time dilation operates continuously throughout your body. This effect reveals that even the simplest measurements of time require understanding how gravity affects the fundamental mechanisms that create duration itself. The Photon clock experiment. Understanding these gravitational effects requires examining the fundamental mechanisms that create time itself. Einstein devised the simplest possible timekeeper to demonstrate how time dilation affects all measurements of duration. This photon clock consists of nothing more than a single particle of light bouncing back and forth between two perfectly reflective mirrors positioned exactly 1 meter apart. Each time the photon completes a round trip from one mirror to the other and back again, the clock marks 1 second. The photon travels at exactly 299,792,458 meters per second, so the round-trip distance of 2 meters takes precisely 149,896,229 of a second to complete. This creates the most basic timing mechanism possible, using only light and mirrors to measure the passage of time. Einstein placed 3 observers in different positions to watch this photon clock in action. The first observer floats motionless in deep space, far from any gravitational influences, holding the photon clock and watching the light bounce vertically between the mirrors. The second observer stands on a mountaintop on Earth, also stationary, but within Earth's gravitational field. The third observer begins falling freely toward Earth from a great height, carrying an identical photon clock while accelerating downward under gravity's influence. Each observer carries precision instruments to measure exactly how long each photon round trip takes. The space observer sees the photon in their own clock travel in perfectly straight vertical lines between the mirrors. Each reflection occurs at precisely the expected time interval, marking seconds with mathematical perfection. The light covers exactly 2 meters during each complete cycle, maintaining the fundamental relationship between distance, speed, and time that defines the photon clock's operation. From this reference frame, the clock behaves exactly as designed, with no complications or distortions affecting the measurement. The situation becomes more complex when the stationary observers watch the falling person's photon clock. The space observer and hilltop observer both see the falling person's clock from their external perspectives, watching as the light traces diagonal paths instead of straight vertical lines. As the falling person accelerates downward, their clock moves continuously in the same direction as their motion. The photon must travel diagonally to reach the lower mirror, then diagonally again to return to the upper mirror, creating triangular paths that cover significantly more distance than the simple vertical bounces seen in stationary clocks. These triangular light paths make the photon travel a longer distance during each timing cycle. The hypotenuse of each triangle exceeds the simple vertical distance between mirrors, forcing the light to cover additional space while maintaining its constant speed of 299,792,458 meters per second. Since the photon cannot travel faster to compensate for the increased distance, each round trip takes longer to complete. The falling person's clock appears to run slower as measured by the stationary observers, even though the falling person sees their own clock operating normally. The triangle size increases dramatically as the falling person's velocity increases. Objects falling toward Earth accelerate continuously under gravitational influence, reaching higher speeds as they descend from greater altitudes. Higher velocities create larger triangular paths for the photon to follow, stretching the duration of each timing cycle even further. The relationship follows precise mathematical rules, with time dilation effects becoming more pronounced as the falling velocity approaches significant fractions of light speed. Objects closer to Earth's center experience stronger gravitational acceleration, creating more dramatic time dilation effects at lower altitudes. A person falling from 1,000 kilometers above Earth's surface accelerates more slowly initially than someone falling from 100 kilometers altitude, but both eventually reach tremendous velocities that produce measurable time dilation. The gravitational field strength increases as objects approach Earth's center, causing continuous acceleration that translates directly into observable time effects for any clocks carried by falling objects. The hilltop observer occupies a different gravitational environment than the space observer, creating an additional layer of time dilation between their respective measurements. Earth's gravity affects the hilltop observer's clock, causing it to run slightly slower than the space observer's clock due to the stronger gravitational field at Earth's surface. This means the hilltop observer sees both their own time passing slower relative to space and the falling person's time passing slower relative to their hilltop position. The gravitational hierarchy creates multiple levels of time dilation operating simultaneously. The Atomic Clock Ensemble in Space mission, launched in April 2025, can measure these infinitesimal time differences with unprecedented precision. The mission features two complementary atomic clocks, Pharaoh, a laser-cooled cesium clock, and the Space Hydrogen Maser. Together, they achieve timing accuracy so precise that they would lose only 1 second every 300 million years, according to Luigi Cacciaputti, an ESA physicist who helped build and launch the device. This extraordinary precision allows scientists to detect gravitational time dilation effects that would have been impossible to measure with earlier technology. The photon clock experiment demonstrates that time dilation affects all types of clocks equally, whether mechanical, electronic, or biological. Mechanical clocks with gears and springs slow down because the physical processes driving their mechanisms experience time dilation. Electronic clocks slow down because the electrical oscillations that control their timing circuits are subject to the same tempo effects. Atomic clocks slow down because the quantum transitions in their atoms occur at altered rates when time itself passes differently. Biological processes operate like extremely complex clocks, with chemical reactions and cellular activities following precise timing patterns. These biological timing mechanisms slow down just like mechanical or electronic clocks when subjected to gravitational time dilation. DNA replication, protein synthesis, metabolic reactions, and neural activity all occur at altered rates depending on the gravitational environment and motion of the organism experiencing them. The most stunning realization emerging from this analysis is that different parts of your body age at measurably different rates due to gravitational time dilation. Your head sits approximately 6 feet farther from Earth's center than your feet, placing it in a slightly weaker gravitational field where time passes faster. The cells in your brain age approximately 90 billionths of a second faster per year than the cells in your feet. While this difference seems negligible, it demonstrates that time dilation operates continuously throughout your body, creating a gradient of aging rates from head to toe that persists throughout your entire lifetime. These profound effects of Einstein's theories extend far beyond laboratory experiments and space missions. The same principles that govern photon clocks and atomic timepieces also control the precise timing systems that enable modern technology to function with extraordinary accuracy. GPS satellites provide the most widespread practical application of these timing principles, with every smartphone navigation system performing relativistic calculations millions of times daily. These satellites orbit approximately 20,000 kilometers above Earth's surface, traveling at roughly 3.874 kilometers per second as they circle the planet. At this altitude and velocity, both special and general relativistic effects create significant impacts on the atomic clocks that enable precise positioning calculations. The high orbital velocity creates time dilation effects that make satellite clocks run slower than identical clocks on Earth's surface. Special relativity predicts that clocks moving at high speeds experience time at a different rate compared to stationary observers. GPS satellites experience this velocity-induced time dilation continuously as they race through their orbital paths at nearly 14,000 kilometers per hour. This effect causes the satellite clocks to lose approximately 7 microseconds per day compared to ground-based timing standards. Gravitational time dilation creates the opposite effect on GPS satellite clocks. The weaker gravity at orbital altitude makes satellite clocks run faster than Earth-based clocks because they sit in a shallower region of Earth's space-time valley. General relativity predicts that clocks in weaker gravitational fields tick at faster rates than clocks in stronger fields. This gravitational time dilation effect causes GPS satellite clocks to gain about 45 microseconds per day relative to clocks at sea level. These competing relativistic effects create a net time difference of approximately 38 microseconds per day. The gravitational speedup of 45 microseconds per day, minus the velocity slowdown of 7 microseconds per day, produces a net gain of 38 microseconds daily for satellite clocks compared to Earth-based standards. This seemingly tiny discrepancy would accumulate rapidly without corrections, creating massive errors in position calculations that would render GPS completely useless for navigation purposes. The precision required for GPS accuracy demands timing synchronization accurate to about 17 nanoseconds to achieve navigational accuracy of 5 meters. Modern GPS systems routinely provide positioning accurate to within a few meters, requiring even more stringent timing controls. Without relativistic corrections, GPS systems would accumulate positioning errors of roughly 11.4 kilometers per day, making the technology worthless for any practical navigation application within a matter of hours. Engineers solved this relativistic timing problem by adjusting satellite clock frequencies before launch. The atomic clocks aboard each GPS satellite operate at 10.22999999543 MHz instead of the standard 10.23 MHz frequency used by ground-based atomic standards. This frequency offset of approximately 4.465 parts in 10 billion compensates for the predicted relativistic effects, ensuring that satellite clocks maintain synchronization with Earth-based timing standards despite experiencing different rates of time passage. The orbital mechanics of GPS satellites complicate these relativistic corrections further. Satellites follow elliptical rather than perfectly circular orbits, causing their distance from Earth and orbital velocity to vary continuously. These variations create fluctuating time dilation effects that change throughout each orbital period. The official GPS specification document ICD-GPS 200C includes detailed procedures for accounting for these orbital variations and their impact on relativistic timing corrections. GPS technology development began in 1955 with the initial concept of using atomic clocks in space for navigation purposes. The practical implementation required decades of engineering work to create atomic clocks stable enough to operate in the harsh environment of space while maintaining the extraordinary precision needed for accurate positioning. Modern GPS satellites carry multiple atomic clocks as backup systems, ensuring continuous operation even if individual clocks fail or drift from their nominal frequencies. The 2025 generation of GPS satellites incorporates even more sophisticated timing systems that push the boundaries of relativistic correction accuracy. Next-generation atomic clocks achieve stability levels that would lose only 1 second every 300 million years, demanding correspondingly precise relativistic calculations. These improvements enable GPS accuracy measurements down to centimeter levels for specialized applications like precision agriculture, surveying, and autonomous vehicle navigation. Other modern technologies beyond GPS rely on precise timing synchronization and must account for relativistic effects in their operation. Global communications networks use atomic clocks to synchronize data transmission across continents, requiring relativistic corrections for timing standards distributed at different altitudes and latitudes. Financial trading systems depend on nanosecond accurate timestamps to process transactions fairly, incorporating relativistic corrections for clock synchronization between trading centers worldwide. Scientific research facilities like particle accelerators and radio telescopes require extremely precise timing coordination between multiple locations. The Event Horizon Telescope, which captured images of black holes, synchronizes observations from radio telescopes distributed across the globe using atomic clocks that must account for relativistic effects. These timing corrections enable scientists to combine signals from telescopes separated by thousands of kilometers, creating effective telescope arrays with unprecedented resolution. Cellular networks increasingly rely on GPS timing for coordinating communications between cell towers and managing network traffic efficiently. The rollout of 5G cellular technology demands even more precise timing synchronization to coordinate complex antenna arrays and manage high-frequency signal transmission. Network engineers must understand relativistic timing effects to maintain the nanosecond-level synchronization required for optimal 5G performance. Einstein's theories of relativity have become indispensable for technologies he could never have imagined when he formulated his ideas in 1905. The patent clerk, who wondered what would happen if a tram could travel at light speed, created a theoretical foundation for navigation systems that guide billions of people daily. Every GPS calculation, every synchronized communication, and every precision timing measurement proves that Einstein's insights about the nature of space and time remain as relevant today as they were over a century ago. The smartphone in your pocket represents one of the most sophisticated applications of Einstein's relativity theories ever created. Each time you check your location or navigate to a destination, your phone performs relativistic calculations that would have seemed like science fiction to Einstein's contemporaries. These corrections operate invisibly in the background, but they represent just one application of time dilation effects that scientists can observe and measure. The most dramatic demonstrations of Einstein's predictions occur in environments where particles approach the ultimate speed limit of the universe itself. Particle accelerators, time dilation at light speed. The Large Hadron Collider at CERN accelerates protons to velocities so close to light speed that Einstein's time dilation effects become dramatically visible in every experiment. This massive machine, stretching 27 kilometers beneath the Swiss-French border, pushes charged particles to 99.99991% of light speed before smashing them together in high-energy collisions. At these extreme velocities, particles experience time at radically different rates compared to the scientists observing them from the laboratory reference frame. The LHC's ability to generate collisions at energies of 13 teraelectronvolts creates conditions where Einstein's predictions about time become essential for understanding what happens inside the detector chambers. Unstable particles that would normally decay in microseconds survive dramatically longer when accelerated to near light speed, allowing physicists to study fundamental building blocks of matter that would otherwise vanish before instruments could detect them. The top quark represents a perfect example of this phenomenon. Under normal conditions, top quarks decay so quickly that they exist for only about 5 times 10 to the power of negative 25 seconds, making them nearly impossible to observe directly. When created in high-energy collisions at the LHC, these same particles experience such extreme time dilation that their lifetimes extend enough for sophisticated detectors to measure their properties and decay patterns. Scientists have turned this time dilation effect into a powerful research tool, using extended particle lifetimes to probe the deepest secrets of matter and energy. The CMS collaboration at CERN conducted extensive experiments during the LHC's Run-2 period from 2015 to 2018, analyzing millions of collisions to search for any deviations from Einstein's predictions. These experiments tested whether top quarks behave consistently with special relativity regardless of the orientation of the detector or the time of day when collisions occurred. The results confirmed Einstein's theories with extraordinary precision, showing no evidence of Lorentz symmetry breaking even under the most extreme conditions achievable in terrestrial laboratories. The precision measurements from these particle accelerator experiments provide some of the most stringent tests of Einstein's theories ever conducted. Modern detector systems at the LHC can track individual particles through their entire life cycles, measuring positions accurate to micrometers and timing intervals accurate to picoseconds. This precision allows scientists to observe time dilation effects directly by comparing the expected decay rates of particles at rest with the observed decay rates of particles traveling at relativistic speeds. The measurements consistently match Einstein's predictions to extraordinary accuracy levels. Muon experiments demonstrate time dilation effects occurring naturally in Earth's atmosphere every single day through cosmic ray interactions. Cosmic rays striking the upper atmosphere create showers of particles including muons, which are unstable particles similar to heavy electrons. These muons have a mean lifetime of approximately 2.2 microseconds when at rest, which should allow them to travel only about 660 meters before decaying. Since muons are created at altitudes of 10 to 15 kilometers above Earth's surface, they should never reach ground level based on their short lifetimes and the distance they need to travel. The reality contradicts this simple calculation because muons created in cosmic ray interactions travel at velocities approaching light speed. Time dilation extends their effective lifetimes as measured from Earth's reference frame, allowing them to survive the journey from the upper atmosphere to the surface. Ground-based detectors routinely observe these cosmic ray muons, providing continuous natural demonstrations of Einstein's time dilation predictions. The Frisch-Smith experiment in 1962 measured this effect precisely by comparing muon decay rates at different altitudes, confirming the time dilation factor predicted by special relativity. These cosmic ray muon observations represent one of the most accessible proofs of Einstein's theories available to modern scientists. Unlike the complex experimental setups required at particle accelerators, cosmic ray interactions occur naturally and continuously throughout Earth's atmosphere. Simple detector arrays can measure the flux of muons reaching the surface and compare these measurements with the expected rates based on muon production in the upper atmosphere. The dramatic difference between predicted and observed muon numbers provides direct evidence that time passes differently for particles traveling at high velocities. Advanced detector technologies developed for particle accelerators have revolutionized the precision with which scientists can measure time dilation effects. Silicon pixel detectors can track particle trajectories with spatial resolution measured in micrometers, while sophisticated timing systems measure particle arrival times with precision better than picoseconds. These capabilities allow researchers to observe time dilation effects for individual particles rather than statistical averages, providing unprecedented detail about how Einstein's predictions apply to specific quantum events. The Null 63 experiment at CERN studies radiation processes in strong electromagnetic fields by directing electron beams onto crystalline targets. These experiments investigate how electromagnetic fields affect the timing of photon emission, revealing that this process takes measurable time and can be experimentally influenced. The results provide insights into how time operates at the quantum level, where particle interactions occur on timescales that approach the fundamental limits of causality. Particle accelerators have essentially become time machines that allow scientists to observe the universe's fundamental building blocks under conditions that existed only in the first moments after the Big Bang. The extreme energies and velocities achieved in these machines recreate environments where time dilation effects become dominant factors in particle physics. By studying how particles behave under these conditions, researchers gain insights into the fundamental nature of space and time that cannot be obtained through any other experimental approach. Every cosmic ray interaction in Earth's atmosphere provides natural validation of Einstein's century-old insights about the relationship between motion and time. The muons reaching the surface, the particle tracks recorded in accelerator detectors, and the extended lifetimes of unstable particles all demonstrate that time dilation operates exactly as Einstein predicted. These experiments prove that the patent clerks thought about frozen clock hands has become the foundation for humanity's most sophisticated investigations into the fundamental nature of reality. Yet even these extreme conditions may represent only the beginning of our understanding of how time truly operates at the deepest levels of existence. The future of time. Modern research continues pushing the boundaries of Einstein's theories towards scales and precision levels that reveal new mysteries about the fundamental nature of time itself. Quantum gravity research in 2025 explores how Einstein's theories might require modification at the smallest possible scales where quantum effects become dominant. Scientists work toward reconciling general relativity with quantum mechanics, seeking a unified theory that explains how space-time behaves when quantum gravitational effects become significant at the Planck scale. This represents one of the most challenging frontiers in modern physics, where our understanding of time itself might need fundamental revision. Advanced atomic clocks are achieving time measurement precision that would have seemed impossible just decades ago. The Atomic Clock Ensemble in Space mission, launched by the European Space Agency in 2025, represents the pinnacle of timing technology. According to Luigi Cacciapuoti, an ESA physicist who helped build and launch the device, this technology achieves such precision that it will not lose or gain a second in 300 million years. The ACES system combines two complementary atomic clocks, one containing cesium atoms and another containing hydrogen, working together to produce timing signals with higher precision than either clock could achieve independently. These space-based atomic clocks operate aboard the International Space Station at approximately 400 kilometers altitude, creating ideal conditions for testing Einstein's predictions about gravitational time dilation. The mission compares its onboard clocks with highly accurate ground-based atomic clocks worldwide, searching for tiny deviations that could reveal new physics or provide insights into dark matter models. The expected improvements in measurement accuracy would enhance current gravitational redshift measurements by a factor of 10, opening new possibilities for testing fundamental physics in ways that ground-based experiments cannot match. The ACES mission enables worldwide clock comparisons with precision reaching 1 part in 10 to the power of 17, approximately 100 times better than current GPS-based synchronization methods. This extraordinary accuracy allows scientists to detect geopotential height differences on Earth's surface with 10-centimeter precision, revolutionizing both fundamental physics research and practical applications like improved GPS navigation and telecommunication systems. The mission demonstrates transmission of ultra-stable time signals to Earth with uncertainties as low as 100 picoseconds, enabling global synchronization networks that far exceed current capabilities. Emerging technologies increasingly exploit relativistic effects for applications that extend far beyond traditional physics research. Professor Paul Couillard's team at the University of Illinois developed quantum interferometry tools using extreme color entanglement to enable faster and more precise measurements than classical or existing quantum techniques can achieve. These innovations find ready applications in medical diagnostics, remote system monitoring, and material characterization, demonstrating how Einstein's insights continue spawning practical technologies in unexpected fields. The ACES mission may contribute to redefining the fundamental unit of time itself as optical clocks emerge as the future standard for timekeeping. Current satellite technology cannot handle the precision levels that modern atomic clocks achieve, creating opportunities for entirely new approaches to global time synchronization and fundamental physics research. The mission offers opportunities to probe whether fundamental physics constants remain truly constant over time by comparing ground-based clocks that operate using different atomic transitions. Scientists can monitor whether the fine structure constant that governs electromagnetic interaction strength varies over time. Any detected variation, however small, could indicate new physics involving dark matter, extensions to the standard model, or previously unknown aspects of space-time structure. The ACES mission serves as a laboratory for exploring fundamental workings of the universe through precise time measurements, simultaneously testing both general relativity through gravitational time dilation measurements and special relativity through observations of time passage for objects in relative motion. Modern experiments reveal that gravitational effects influence time in ways that create practical applications Einstein never anticipated. The ACES mission's ability to detect 10-centimeter height differences through gravitational time dilation measurements enables relativistic geodesy applications that improve understanding of Earth's gravitational field variations. These measurements support geological research, climate monitoring, and natural resource exploration by revealing subsurface density variations that affect local gravitational fields and consequently local time passage rates. The precision achieved by contemporary atomic clock technology allows scientists to test whether fundamental constants truly remain constant throughout cosmic time. Variations in the fine structure constant would indicate that the basic parameters governing electromagnetic interactions have changed since the universe began, potentially revealing new physics that connects cosmology with quantum mechanics in unexpected ways. Such discoveries would represent profound extensions of Einstein's work, showing that even his revolutionary insights captured only part of reality's deeper structure. Einstein's simple tram thought experiment launched a revolution that transformed our understanding of space and time, revealed the relativity of simultaneity, demonstrated space-time curvature, and enabled technologies like GPS that define modern life. The ACE's mission represents the latest chapter in this ongoing exploration, using precision timing measurements to probe fundamental questions about the universe that continue guiding physics research. Each new measurement reveals that Einstein's century-old insights about frozen clock hands have become far more than theoretical curiosities. Today, these theoretical insights operate invisibly within billions of devices worldwide, transforming Einstein's tram visualization into practical technology that defines modern civilization. That spring evening in 1905, when Einstein imagined frozen clock hands on a burn tram, has become the invisible foundation supporting smartphones, navigation systems, and communication networks across the globe. The patent clerk's simple thought experiment now guides every GPS calculation, synchronizes global financial networks, and enables precision measurements that probe the deepest mysteries of quantum mechanics. His visualization of time slowing down at light speed created the mathematical framework that makes modern technology possible, proving that the most profound scientific discoveries often emerge from the simplest questions about reality itself.